Yo, what's up, geometry students? We are going to solve some more triangles, only this time we're finding angles. So we have our first triangle here. We can see angle A, B. We're missing side length A. We could go ahead and find side length A right away if we want to. We understand that the Pythagorean theorem can be used to find side lengths of a right triangle that is a right triangle. And we can find that A is 3. Great, so this is a 3, 4, 5 right triangle. Oh, cool. It's one of those special right triangles. And we think this special triangle probably has like these special angles that create it. A lot of us think that a 3, 4, 5 right triangle is created like a 30, 60, 90 triangle, but it's not. Now, the way we do this is we use inverse trig. We are going to plug in a ratio, and the inverse trig function is going to give us an angle. Please make sure your calculator is in degree mode. And we can focus on, let's say, angle B. Now you have 3 options to get this angle B. You can use sine inverse. Now I do sine and then shift 6, -1. Press to the right to bring down. Type in your ratio for the sine ratio of B, which is 4/5. Now, let's say you don't like typing that in. You can go to functions and you can go to sine inverse, and that might be the quickest way to do it for you. Now, what's great about this is that you could just delete the sine inverse, or you could copy and paste it, and then all of a sudden I could type in cos inverse. And if I change it to cos inverse of 3/5, I get that same angle, 53.13 degrees. And if I did the tan inverse, the tan ratio is 4/3, I get that same angle, 53.13. So there is like so many different options for finding your angle measurements. And I would want you to say that it's the sine inverse of 4/5 or 53.13 degrees, ... knowing that it goes on forever. And you could do the same thing with A. Well, you can realize that the sine of A is 3/5. So the sine inverse is giving you that 3/5, that 36.89. You could say the cos inverse of 4/5 gives you that same thing. The tan inverse of 3/4 gives you that same thing. There's so many different options. Or you know that all 3 angles are going to add up to 180 degrees. You already have a 90, so that means these 2 angles add up to equal 90. We could have taken that 90 and subtracted that 53.13 degree angle to get your other angle, 36.869. So there's just a lot of different ways to do it. Cool. Now, I look at this triangle and I see something. I know that I have a triangle 1√3, 2, where the hypotenuse is twice the size of the short. This triangle is scaled to get the 2G4. Well, I should know without using inverse trig that this is a 60-degree angle. This is a 30-degree angle. G is 3, times 2 is going to be 2√3. So we should find G. We should find H. We should find G without having to use Desmos. But let's say we did. No big deal. Here the sine, we could have used the Pythagorean theorem to find G. We'd have 2 squared plus G squared equals 4 squared. We'd have G squared equals 16 minus 4, which is 12. G equals the square root of 12. The square root of 12 is the square root of 4 times the square root of 3, which is 2√3. You could have said sine of G is 2 square root 3/4. Oh, look at that, 60 degrees. You could have said the cos was 2/4. Oh, look at that, 60 degrees. You could say the tangent is 2 square root 3/2. Oh, look at that, you get 60 degrees. If you wanted to look at the other angle, angle H, you would have just said the sine of angle H is 2/4. And all of a sudden you see that that's 30 degrees. So We can use Desmos to check, but we should be able to recognize this triangle and figure out the answers here. Let's go right for the angles. Let's go straight to the angles. Maybe the question is just about the angles and it doesn't have us find the side length. Well, I could say that angle F would be the tan inverse of 6 over 3. I could say angle D is going to be the tan inverse of 3 over 6. You can see that they're reciprocals of each other, these ratios. And you can literally type in tangent of 3 over 6. That's when the opposite is 3 and the adjacent's 6. And you should be able to see the complementary angles if you flip. And you go 6, 3, and you got 63.43. So here we realize that this this triangle where the legs are double each other is not a very nice angled triangle. It's a very interesting angle, 63.434 and 26.565. What's E? You can use the Pythagorean theorem. You could actually use trigonometry if you wanted to. You could scale it. E could be 3 sine of 63.434 if you wanted to do that. But it's probably best just to use the Pythagorean theorem. So that's 9 plus 36. That's 45. That's root 9, root 5. C is the square root of 45. Square root of 45 is the square root of 9 times square root of 5, which is 3 root 5. I recognize this triangle. This is an isosceles right triangle. This is a 1, 1 root 2 right triangle. What type of triangle must that be? A 45, 45, 90 triangle. K is 45, J is 45, and L is 45 times root 2. Sorry, 2 times root 2. Now, if we did the tangent of 2 over 2, we get that 45. If we did the sine inverse of 2 over 2 root 2, we get 45. Different ways to get those angles. We go to question 5, and this question's really just like a trick question. It just shows you how, if your triangles are similar, you're going to get the same angles. Like, watch this. Let me do the sine inverse of n. The sine inverse of n would be the sine inverse of 1 over 5. And I get that. But if I did the sine inverse of k, and I use 2 over 10, well, it's the same ratio. 2 over 10 is the same as 1 over 5. So angle n, 11.536 degrees, is the same as angle k. Wait, sorry. Yeah, n here. K is here. Meanwhile, you could use the cosine of m. Cos inverse, to get your complementary angle, angle M, 78.463. These two angles will add up to be 90. Here's 78.463. And if you wanted to find M, 25 minus 1, so 1 squared plus M squared equals 5 squared, we'd get M squared equals 24. This is root 4 root 6, which is 2 root 6. You could scale it. You don't have to use the Pythagorean theorem again. This is 4 root 6. So just an interesting thing to show similarity. Remember coordinates? Yeah, I remember coordinates. Well, how do you find angles created between line segments and the x-axis? Well, I know that this would be 2 and this would be 3. I could see that if I use the tangent, my ratio of the angle would be 3 over 2. So if I do tan inverse, that's a shift 6, -1, shift down, open up your parentheses, 3 over 2, 56.309 degrees. Well, what happens if we're talking about this angle here with the y-axis? Well, now this would be 2, and this would be 3, which means you would have the complementary angle. You'd have the tan inverse of 2 over 3. 33.69. Or you could just did, these two angles create a 90-degree angle. It's actually an interesting thing that you can see. why the tangent of reciprocals are complementary to each other. And what about this guy with the x-axis? I could see this opposite length is 1, this adjacent length is 4, so I'd say this is the tan inverse of 1/4. Here I'm going to say this is the tan inverse of 3/2, whereas this is the tan inverse of 2/3. Tan inverse of 1/4, and this is the tan inverse of 4/1. See how they're complementary to each other? Smaller angle here, bigger angle here. Cool. Now we're ready to apply everything we know. Whether we are given an angle and we know we can scale said angle and its ratios, sine and cosine, with a hypotenuse of 1 so that we could see a scale factor, or you could use trigonometry your other way, giving you the length of x of this tree's height is going to be the sine of 35 times 47 over the cosine of 35. Here, the next one, you could see we are given the angle of 51 degrees. I personally always start with a smaller triangle and scale it. I think it works for every triangle out there. And I know that the cosine of 51 over 1 can represent the side lengths of a right triangle. I could see the scaling is times 8. So if I see that the wire's length is 8 feet, and I want to find how far from the foot of the stop sign is the stake, so this adjacent length, I could say it's 8 cosine 51. Sometimes you'll have to draw a picture. We have a distance from a base of a tree is 50 feet. The angle of elevation is 60 degrees. What's the height of the tree? Oh, I know a 30, 60, 90 triangle. Small, medium, large, 1√32. I can see that the scale factor is times 50, so that I know that the height of the tree must be 50 times √3. But we have situations where you might ask for an angle. A person is 2,000 feet horizontally from a launch pad. When the rocket is 5,000 feet in the air, what is the angle of elevation? That refers to the angle where the 2,000 is adjacent and the 5,000 is opposite. So we can understand that the ratio tangent would be 5,000 over 2,000, or 5/2. So I know my angle would be the tan inverse of 5/2. Remember, you would not type in tangent 5/2 because this is actually referring to 5/2 as an angle measurement. So you don't want 0.043. We want tan inverse, plug in a ratio, get an angle, versus plug in an angle, get a ratio, the other way around. So I can see tan inverse of 5/2 is 68.19. And then question 12, a person is spying on someone from the top of a building that is 80 feet tall. Here's our person spying on somebody. The person on the ground is 200 feet away. What's the angle of depression? Well, the angle of depression actually refers to this angle here. Now, it's not going to be a big deal, but we realize that an angle of depression, geez, I can't write. The angle of depression is not this angle created with the guy's sight line and the building. It's actually created with the horizon that goes down to his sight line. So from the horizon to the sight line, we could see that the opposite is 80 and the adjacent is 20. I don't want the tan inverse of 200 over 80. I actually want the tan inverse of 80 over 200. I said 20, I meant 200. I want this angle here, which is 21.801. Okay, that's it. We're done. We're done with trigonometry. How did it go? We'll see. We got to review next class, test the following. See you out there. Peace.